Alrighty, gang. Good morning and welcome back to Calc 2. I am glad to say my voice has mostly returned and life is on its way to being back to normal. Still a little gravelly and a little grumpy, but we gonna get through this shit. We gonna get through this shit just fine. Today, we are going to talk about work, which is a concept from physics that can be thought of in a handful of different ways. And the way I would like you to think of work fundamentally is as the amount of energy required to move an object. And I think it is also worth mentioning that work as a scalar quantity, for those of you who are familiar with the distinction between scalars and vectors, can be positive, can be zero, and can be negative. So if, for example, I am lowering my phone like this, I'm doing negative work because I'm going along with the force of gravity. On the other hand, if I raise my phone like this, fighting the force of gravity, I do positive work. And that is a distinction that's not always immediately clear to those who are first encountering the topic. The other thing that is a little bit counterintuitive in this section is the distinction between mass and weight. So before we get into any of the calculations, theorems, definitions, and we'll do plenty of that, I just want to talk for a second about the difference between mass and weight, because intuitively we usually think of them as being kind of the same thing, right? When I say I weigh 100 kilograms, most of us think that that's the same thing as saying my mass is 100 kilograms. In fact, if I tell you that I weigh 100 kilograms, I'm lying a little bit. It is true that my mass is about 100 kilograms, but my weight is not, because weight is a force. Mass is a measure of the amount of matter in an object. Another way to think of that is mass is a measure of your momentum, right? Your resistance to changes in velocity. And in our daily experience, they feel like the same thing. But if you send me up on the space station, I'm weightless. My mass is still 100 kilograms. So this is one of those things that we might not realize at first require some distinctions. It all has to do with units of measurement. So kilograms is the SI, or standard unit of measurement for mass. And pounds is the imperial unit for weight. And we often think of it like you can convert from one to the other, multiply by 2.2. It's a reasonable thing to do here on the surface of the Earth, where you can readily interchange the ideas of mass and weight in your day-to-day lives. But when we get to doing calculations here from this physics point of view, it's important to make the distinction. So I want to talk just a teensy bit about that. Here we are. Let's get started in the actual stuff. This is MAC 2312, section 004, which is calculus 2. Today is the 19th of January, 2022. We're talking about this concept of work. Section 6.4. If you look for the definition of work, let me show you here. You'll see a few different things. All right, so work is the energy transferred to or from an object by the application of a force along a displacement. But this is not the only definition of work. And the main thing that I want to point out when it comes to this is the definition we'll use. It's a perfectly fine way to think of things. It's a force times a distance. The unit for work, the SI unit for work, is the joule. Now, joules are usually thought of as the unit for energy. Those of us who've taken physics are familiar with talking about energy in terms of the units joules. And there is a very important theorem in physics called the work energy theorem. Is there a Wikipedia page for this? Oh, just have to skip down to work energy theorem. Right. Close enough. All right, it says that the work is the rate of change for the energy. That's the basic idea. So the work done by all forces acting on a particle is equal to the change in kinetic energy. And that assumes that there's no thermodynamic loss, right? No heat loss or friction, stuff like that. But what this basically says is that work is equivalent to energy. Certainly they're measured in the same units. So the work that you do is the energy that the object had at the end of the process minus the energy that the object had at the start of the process. So yeah, work and energy are in a very real sense equivalent. Okay. The reason I mention all this stuff between mass and weight is because the classic examples that we're calculating work with have to do with like lifting an object, right? The mass of the object, if you want to find the force due to gravity, needs to be multiplied by gravitational acceleration. So here on the surface of the Earth, if I drop something, it falls towards the Earth, it begins to accelerate towards the center of mass of the Earth at the rate of 9.8 meters per second, which means that for every second it falls, it gains 9.8 meters per second of speed, right? So meters per second, that's a measure of speed, how fast something is moving. It goes 9.8 meters in 1 second. When we say that gravitational acceleration is 9.8 meters per second squared, or 9.8 meters per second, that means that every second, the object speeds up by 9.8 meters per second. If you want to go from the mass of an object to the force that gravity is applying to that object, according to Newton's second law, you need to multiply by the acceleration. So if I tell you this object weighs 0.02 kilograms, then to find the force acting on it due to gravity, you would multiply that 0.02 kilograms by 9.8 meters per second squared, and that would give you the force. If I tell you that this object weighs something like 0.01 pounds, then that is already a force. So a little discussion of mass versus weight. Mass formally is the measure of the amount of matter in an object. The amount of stuff that's there. And by stuff, what I mean, protons, neutrons, electrons, right? At the atomic and subatomic scale, it's the amount of stuff that's there. This can also be thought of as the resistance. It's the resistance to changes in velocity, right? It's momentum. Mass, your momentum is mass times velocity. So if you want to talk about how massive something is, one way to measure that is to see how hard it is to push the damn thing. And notice here, there's nothing about weight or force. Your weight, this is the force with which gravity pulls you, or pulls an object to the center or towards the center of the Earth. So these are fundamentally different quantities. If you want to know, right, so your weight, which you usually think of, since it's America, in pounds, if you want to get your mass from your weight, the imperial unit for mass is not the kilogram, right? That's the SI unit for mass. I have this here. So the SI unit for this is the kilogram. The imperial unit for mass is the slug, which is a very silly word. I'm not sure who the hell chose that. I can't explain it, but yeah, the SI unit for mass is the kilogram. That's the one that we're all familiar with. If you want to get your mass in imperial units from your weight in pounds, you would need to convert from pounds to slugs. The upshot is weight is a force, mass is not a force. If you want to, so by Newton's second law, the force on an object, and usually we'll be talking about force due to gravity, the force on an object is equal to its mass times its acceleration. And here is your mass, and A here is your acceleration. And the reason this is important for us, again, is because in this section on work, we will need to know the force on a number of objects, usually due to gravity. And if that object's heaviness, if you like, is given as a mass, then you need to multiply by the acceleration due to gravity, which is usually estimated as 9.8 meters per second squared. If the heaviness of that object is given as a weight, then that's already a force. Okay. So here's the mathematical definition of work that we're going to use. The work done by applying a constant force F over a distance, we call it X, is the force times the distance. All right, this is the definition that we will use. In other words, work, W, is equal to the force times the distance. The SI units, standard units for force, is what you get by taking the SI units for mass, kilograms, and the SI units for acceleration, meters per second squared. So this would have units kilogram times meters divided by second squared, kilogram meters per second squared, which we call the Newton. Right, so the units here are kilogram meters per second squared, and that's called 1 Newton. If you take those units, kilogram meters per second squared, i.e. the Newton, and you multiply by a distance, the SI unit for distance is meters, then you have kilograms times meters per second squared times meters. That's kilogram meters squared per second squared, which we call the joule. Okay, so the SI units, let me just add here. SI units for mass. And so it's the kilogram for acceleration. This is meters per second squared. Distance, units for distance are just meters. Is there anything else I'm leaving off there? Oh, and for force, that would be kilograms times meters per second squared. So that's kg m over s squared, which we call the Newton. Right, in honor of Isaac Newton. All right, most of the time it's nice to work in SI units, but some of the problems in the book do have imperial units, like where something's weight is given as a weight, right, in pounds instead of a mass. That's okay. The SI units for work. Again, is a force, which is newtons, times a distance, which is meters. This is called the joule, which is Newton meters or kilogram meters squared per second squared. The imperial units is the foot-pound. Right, pound is force, feet for distance. So force times distance or distance times feet is pounds times feet. Some of your problems will ask for answers in foot-pounds, and those problems will give you the setup in force, weight, pounds, and distances as feet. The problems will ask for your answers in joules, and those will give you your setup in SI units, kilograms, meters per second squared, and so on. Okay. Yes, foot-pounds, FT LBS. All right. I'm be the first to say this is a math class, not a physics class. I'm going to try to not beat you guys up about units, but some of these are just things that you want to know to avoid getting stuck on some of these problems. But if you leave units off in your calculation on the test or something like that, I'm not going to beat you up over it. Okay. Any questions about the differences between mass and weight? So my mass is always 100 kilograms. On Earth, my weight is 220 pounds. On the International Space Station, my weight is 0 pounds. On the moon, my weight is something like 160 pounds. Your weight changes depending on where you are. Your mass never changes. It's always the same. And the key to converting from a mass to a force is to multiply by the acceleration. Acceleration due to gravity, let me add that in here. On Earth, is called little g, and it's 9.8-ish meters per second squared. So if I want to find my weight in newtons, right, I could do that, the SI unit for force, and weight is a force. If I want to find my weight in the SI units, I would take my mass of 100 kilograms and multiply by acceleration due to gravity, which is 9.8 meters per second squared. So that would be what, 980 newtons. That is my weight in SI units, which is different than my mass. Yeah, exactly. Weight changes because gravity changes, right? On the moon, gravity is much weaker than on the Earth. So my weight on the moon is much less than my weight on the Earth. my mass is the same in both scenarios. And if I were floating out in space, I would be weightless. My weight would be 0, but my mass would still be 100 kilograms. Cool stuff, right? Kind of weird, kind of mind-blowing. But yeah, mass and weight, different things. So let me pop open your textbook. We can grab some examples to play with. The big thing in this definition I want you to be mindful of here is that we're talking about a constant force, right? So you can calculate work by multiplying the force times the distance, but only if that force is constant. If that force is not constant, then we'll end up doing an integral. So maybe before I, oh no, we'll do a simple example first, okay? Yeah, here we go. So first example, how much work is done lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high? This kind of feels like middle school physics, but trust me, it will get more interesting. So paraphrasing, how much work is done lifting a 1.2 kilogram book up by 0.7 meters? This is not terribly hard because everything is given to me in SI units. The mass is given in kilograms. The distance is given in meters. And we know that work is equal to the force times the distance. So the force here, in this sense, F equals ma. The force here is the mass times the acceleration, and the distance is still this x. The mass of that book is 1.2 kilograms. The acceleration due to gravity is 9.8 meters per second squared. And the distance I'm lifting is 0.7 meters. So it's 1.2 kilograms, the mass, times 9.8 meters per second squared, the acceleration due to gravity, times 0.7 meters, the distance I have to lift the book against the force of gravity. That's okay. What we're doing is calculating the work done in lifting a 1.2 kilogram book up 0.7 meters. And the big deal is that work is the force times the distance. To get the force that we have to apply to this book to lift it, or the force that we're fighting, it's really the right way to think of it, the force that we're working against, you have to take its mass and multiply by the acceleration. The acceleration due to gravity is 9.8 meters per second squared. So I'm leaving off the units, mass times acceleration times the distance, and then I'll use a calculator to do the computation. We get 8.232 joules. That's the other. All right. Like I said, it kind of feels like middle school physics, right? You're just multiplying a couple numbers. Notice something that's not mentioned here. How long I took to lift the book. Now, if I ask you, how much work does it take to climb a mountain in 10 days versus climbing that mountain in 10 minutes, you might feel like it's harder to climb the mountain in 10 minutes. And this is where we have to separate our intuitive understanding of the word work from the formal definition of the word work. Intuitively, it's more work to climb the mountain in 10 minutes, but really you're going to use the same amount of energy, right? You're just going to use it over a longer period of time if you do it in 10 months instead of 10 minutes. So the amount of time it takes to do something has no bearing on the work. The work is independent of how quickly you do the thing. I'll say that again because it's relevant for one of your homework problems. They try to trip you up a little bit. The amount of work is independent of the time spent doing the motion. It does not matter how fast you do something. It just matters how hard you have to fight a force, right? How hard the force that is working against you is pushing against you. Okay, these get more interesting. If the force is not constant. Oh, good question, Quinn. Sig figs. So here I'm using full precision for the numbers that I'm working with. We're told to assume G is 9.8. It's really not. And in fact, it's different in Florida than it is in Colorado. It depends on how far you are from the center of the earth. Round where they tell you to round, right? Sig figs, no, I'm not, again, not a physics class. I'm not going to beat you up on sig figs. But do pay attention to where the questions ask you to round, and do not round until the very end. So do your calculations in full precision until you get to the end of the problem, and then round to wherever they tell you to round. All right. So yeah, these calculations get harder if the force is not constant. That's an interesting fact. Gravity we think of as being a constant force, but really it's not, right? You know, from Newton's law of gravitation, that it's proportional to the reciprocal of the square of the distance between the two objects. Here on Earth, we just never go far enough from the center of the Earth for it to really get a lot different from 9.8. But there are many other scenarios where you encounter forces that do change. A good example of this is a spring, right? So this law discovered by a physicist named Hooke back in, I think, the 16th or 17th centuries, 1600s. So if I take a spring, for example, the force required to compress or stretch a spring from its natural length increases the further you stretch or compress it. This is something we've probably all experienced, right? This is called Hooke's law. So if I take a spring, right, here's a wall, here's a floor, here's a spring attached on one end to that wall. And I've got something over here attached to the spring, whatever. This is sitting at its natural length. Call that, this is the natural length. if I want to pull this out, the amount that the spring fights me gets higher and higher the further and further I pull. You've probably experienced this with a slinky, right? As you keep the slinky like really slack right here, it doesn't fight you at all. But as you try to stretch it out further and further, it wants to pull back together more and more. What Hooke's law says is the force from a spring, so the force with which a spring resists compression or stretching from its natural length is proportional to the distance it's being stretched or compressed. Right, so if I wanted to stretch this guy, say out to here, let me draw it in a different color. And I want to stretch it out by X meters. Past its natural length, the force that this spring is pulling back with is equal to a constant times that distance. All right, so there's a force pulling back. Because I've stretched this thing, if I were to let go, it would go like boom, back, right? And it would actually bounce back and forth. That's your natural harmonic oscillator, assuming the floor is frictionless. Compressed / stretched. In other words, after being. So I'll reread the whole thing of Hooke's law. The force with which a spring resists compression / stretching from its natural length is proportional to the distance it's being stretched or compressed. Proportional means equal to a constant times, right? If you took college algebra here, we have a medium length section on proportionality. So in other words, if I'm trying to pull a spring, it fights me more and more the further and further I pull it. And it's a linear, the amount it fights me is a linear function of how far I pull or push. K here is called the spring constant. K is a constant, does not depend on X. So some springs are very loose, think like a slinky. Some springs are incredibly tight, think like the springs over the shock absorbers on your car, right? I could sit on one of those and it wouldn't really compress. So the hardness of a spring, the spring's resistance to stretching or compressing, is measured by the spring constant. If the spring constant is very small, then you've got something like a slinky that's very easy to stretch out and compress. If you've got a spring that is very hard, then K will be very large, and that is a spring that is very hard to stretch or compress. And there are limitations to Hooke's law, I should say, right? Everybody, again, who's had a slinky has broken a slinky, right? You pull it too far and then it doesn't want to do its thing anymore. Hooke's law only works if you stay within the limitations of that spring. Hooke's law breaks down if you break the spring. It has to do with the material properties of the stuff the spring is made out of, and we're not going to go into that. So every time you see a Hooke's law problem, we will be assuming that Hooke's law applies. Every time you see a spring problem, we will assume that that spring is still obeying Hooke's law. All right. Can I just see, I'm curious, I don't know how many people here have taken Physics 1. Could you give me a react and zoom, thumbs up, whatever, any react and zoom, if you have seen Hooke's law before? Okay. Yeah, and I think it's pretty common to take Physics 1 at the same time as Calc 2. So if you haven't seen it before, don't stress, you certainly will see it. So what I would like to do now is calculate the work that is done if I want to stretch out a spring or compress a spring. Yeah, it's a good thing. It's a good thing. Physics and calc go together like peanut butter and jelly. So I'll grab again an example from the textbook. Let's see how much. Force of 40 newtons is required to hold a spring that's been stretched from its natural length 10 centimeters, length 15 centimeters. How much work is done stretching spring from 15 to 18 centimeters? All right. So force of 40 newtons is required not to stretch, but to hold a spring with natural length 10 centimeters at 15 centimeters. So this is a measure of the spring constant. This is a measure of how stiff the spring is. They're saying if you stretch this spring out 5 centimeters beyond its natural length from 10 to 15, in order to hold that spring there, you need to hold it with 40 newtons of force, or the spring wants to go back with 40 newtons of force. So this is a measure of how stiff the spring is. They ask how much work is done in stretching the spring from 15 centimeters to 18 centimeters. Was that the figure we gave, 15 to 18? Yeah. Okay. So first, let's try to learn a little bit about this spring. Let's try to find the spring constant for this spring. Then we're going to talk about how to calculate this work. It's not going to be just a multiplication problem because the force is not constant. Now I'm going to kind of go through a derivation here. I'll do it as gently as I can, and then I will show you how to do the general thing. So by Hooke's law, the force from the spring F is proportional to the distance x it has been stretched from its natural length. So the distance that I'm going to be talking about here is not 15 centimeters or 10 centimeters. The natural length is 10 centimeters, And to hold it at 15 centimeters requires 40 newtons of force. That means it's been stretched 5 centimeters. Let's write down the Hooke's law equation, F equals Kx. And then let's plug in the bits we have. The force to hold it at 15 centimeters is 40 newtons. K is the thing I want. The distance x that it has been stretched from its natural length is 5 centimeters. Now here's the rub. This is always the case with physics or real world problems in general. If you